Hi everyone, I hope you all are having a nice afternoon. My name is Mira Varma and today I am going to be talking about a case study of the energy momentum tensor, the D-term, and long-range forces in a classical model of the proton. This presentation is based on my recent paper, Effects of Long-Range Forces on the D-term and the Energy Momentum Structure, co-authored with Professor Schweitzer. The energy momentum tensor can be studied using generalized proton distribution functions in hard exclusive reactions and are of interest because they contain information about the basic properties of a particle, mass, spin, and the D-term. Although the D-term is far less known than the other properties of a particle, it is of equal importance since it describes the internal forces inside the proton. In this study, we use the classical model of Bernoulli to understand the impact of long-range forces inside the proton. Historically, in energy momentum tensor property studies, only short-range forces were accounted for. In this model, the Poincaré stresses are generated dynamically in a local relativistic classical field theory. Even though the model employed is classical, it is well suited for our purposes as it allows us to investigate the impact of long-range forces without worrying about the technical difficulties that arise from models using quantum field theory. We will later show that our results for the D-term are general and can be applied to more realistic models. In this research, we use Bernoulli's classical model as I mentioned before. This model consists of dust particles in a spherically symmetric region of radius r bound by three fields: a massive scalar field phi, a massive vector field v mu, and an electromagnetic field a mu. The particles couple to these fields via the coupling constants g sub s, g sub v, and e. These classical field equations are the first four equations on this slide, and they are relativistically invariant. The second term to the left of the equal sign in the first equation is the scalar phase space distribution. Please note that we used h bar equals c equals 1. The parameters m sub s and m sub v correspond to the sigma and omega meson masses used in nuclear models. The equation at the bottom of the slide is the energy momentum tensor in its full form. The graphs on the right show, respectively, the density of matter, scalar potential, vector potential, and Coulomb potential as functions of r, where the potentials are multiplied by their respective constants. In the density of matter graph, there is a drop at r equals 1.05 femtometers. In this graph, you could see that the Coulomb potential is 2 orders of magnitude smaller than the vector and scalar potentials. This will not be the case at larger r. In order to analyze the pressure inside the proton, we use the stress tensor, the Tij component of the energy momentum tensor as shown earlier, and decompose it into a traceless part associated with the shear forces and a trace associated with the pressure. This relation is shown in the first equation of this slide, where e to the ri is the unit vector in the radial direction. If we solve for the individual contributions of the pressure, we get the equations at the bottom of the slide. When we integrate over space, we get the values depicted. This is shown graphically as well. Even though the contribution from the Coulomb force is minuscule, it is not negligible. If this contribution did not exist, the system would implode. It is important to note that the pressure inside the proton obtained from this model is an order of magnitude smaller than in the chiral quark-soliton model. This is because we are working with residual nuclear forces, which are about an order of magnitude weaker than the strong forces among quarks inside the proton. The model results of total pressure and shear force are given by the first two equations on this slide. Notice that the dust particles do not contribute to S of r and P of r. The second equation shows that the pressure and shear force are not independent. We introduce this equation now as it will be important when we discuss the D-term later on. As we can see from the first graph, the scalar field makes the largest contribution to the shear force. The shear force has a maximum at r equals 0.711 femtometers, which is within 0.1% of the charge radius, 0.714 femtometers. The von Laue condition is listed at the bottom of the slide and is a necessary but not sufficient condition for stability. The von Laue condition requires that internal forces inside a system must balance each other. The second graph shows how the von Laue condition is satisfied in our model. This model is different from other studies because this model includes long-range Coulomb forces. In previous studies of strongly interacting systems governed by short-range forces, 3 common features were observed. The first feature is that the shear force is always positive. The second feature is that the pressure has one node at R0, with P of R is greater than 0 when R is less than R0, and the pressure is less than 0 for R is greater than R0. This property arises from the fact that the pressure must have at least one node to satisfy the Volnau condition, and the ground state exhibits a single node. Finally, the combination of 2/3 of the shear force plus the pressure, which is normal force per unit area, is always positive. From the T00, S of R, and P of R equations, we obtain the long-distance behavior when R is greater than 2 femtometers. The dots in these equations indicate subleading, exponentially suppressed contributions from the strong interaction fields. We observe that T00 is always greater than 0, which is in agreement with all prior studies. The 1 over R to the 4th decay of T00 guarantees the convergence of total energy. The mean square radius of the energy density, however, diverges. In previous slides, we saw that at small r, S of R was always positive, which was in agreement with past studies. Here, we see that S of R is negative at large r. This is because S of R changes sign, in other words, has a node at R equals 2.144 femtometers. Previously, we saw that P of R obeyed the expected pattern, positive P of R in the inner region, a single node, and negative pressure in the outer region. However, here we see that P of R is positive at large r. This is because at R equals 2.394 femtometers, the pressure has a second change of sign, in other words, a second node, and then remains positive. We also see that the normal force, 2/3 S of R plus P of R, is positive at small r, confirming what we expected, but after exhibiting a node at R equals 1.881 femtometers, it remains negative. These 3 long-range features are important because after the appearance of the nodes, the respective densities have signs opposite to those expected from previous studies. It is important to note that the shear force and pressure are small in the regions where we see these new features. The D term in our model has 2 equivalent definitions in terms of shear force and pressure. This equivalence arises from the energy-momentum tensor conservation. We use n equals 3 here for the space dimension. Because of the asymptotic behavior of S of R and P of R at large r, the expressions for the D term diverge at large distances. The fact that the D term diverges is a new feature that has not been encountered in previous studies. In previous studies, the D term converges in strongly interacting systems. The 2 graphs on the right of R to the 4th times pressure and shear force respectively depict a close approximation for the D term. From these graphs, we can see that the D terms diverge due to the small, but not negligible, Coulomb contribution. One cannot ignore this Coulomb contribution as it communicates the presence of an electric charge. In order to obtain a value for the D term, we adopt a regularization prescription. To obtain a finite result for the D term, we observe that in a theory where the energy-momentum tensor is conserved and the integrals defining dp and ds exist, we can write the D term as a linear combination of dp and ds, which is the first equation shown in the slide. d zeta is divergent for all zeta except for the one value where zeta equals zeta reg. We choose d reg equals d zeta reg, where d reg is finite. Zeta reg depends on the number of dimensions, little n equals 3, and the power, capital N equals 4, in the long-distance asymptotics of S of R and P of R. These long-distance asymptotics are given in the 3rd bullet of this slide. It is important to note that we obtain capital N from Maxwell's equations for a general number of dimensions. Considering the prefactors of dp and ds, we get the following value for zeta reg, as shown in the last bullet. This regularized D term is finite, negative, and can be expressed in terms of P of R and S of R as shown in the final equation. As mentioned before, since we are working with residual nuclear forces, we expect values an order of magnitude smaller than in the quark-soliton model, which is what we found. This regularization method removes the divergences from dp and ds in an efficient way. The long-range QED contributions exactly cancel out in the linear combination 6p of r plus s of r. This regularization method also preserves the negative sign of the D term that has been observed in all prior studies. This result is not unique. It would be interesting to use other methods to regularize these divergences. Unfortunately, I don't have the time to go through this in detail, but I wanted to show a graph comparing the D term calculated using effective field theory techniques with our calculated D term. For negative T is less than 10 to the negative 6 giga-electron-volt squared, the QED results are the same as our results. In our paper, we used a classical model which includes long-range forces through the Coulomb contribution to calculate the D term. We found that the D term diverges, in direct contrast to the convergent results of previous studies. The classical model was not an impediment. It allowed us to investigate properties affected by long-range forces without worrying about technical difficulties in more complicated quantum systems. The form factors A of t and J of t are also affected by QED long-distance effects, but were not studied here since they are fixed at A of 0 equals 1 and J of 0 equals 1/2, whereas the D term in general is not constrained. We do not currently have a definite method of calculating the D term in a system with long-range forces. One answer to this question is with our regularization scheme. This regularization scheme is acceptable because it yielded a finite result, preserved the negative value of the D term in agreement with other studies, and it serves as a good, reasonable calculation of D of t, as shown in the graphs on the previous slide. An important takeaway from the study is that long-distance QED effects become noticeable at very small t, when negative t is less than 10 to the negative 6 giga-electron-volt squared. Since these effects are so small, are they measurable? This will be left to future studies.